Hey guys, Forecaster Nate here, and in this playlist, we're going to be taking a look at how to properly forecast for my US MVP program. Without further ado, don't forget to like and subscribe. Let's get right into this. What you are currently looking at is a model map. These are what scientists at SPC and NOAA use to determine forecasts. Now, these forecasts have something called a runtime. A runtime is when the last model was generated. As you can see off to the right, there are multiple amounts of hours, typically split apart by 6 hours from each other. For example, this is hour 6, this is hour 78. Now 6 is going to be from now, or the closest to now, and then it goes farther out, the farther down this list you go. However, as a quick note for anybody who is jumping straight into this, typically past hours 210 and 292, unless it is compared with other models and is completely accurate, they are typically not accurate past 192 and 210. That is typically where I stop looking at model forecasts for at least a few days until the system moves forward. Now, let's go ahead and look at precipitation and moisture. Over here on our left, you will see these 4 buttons, and then there will be more buttons once you click on those. These are going to be to change your model product. Now, your model product, for example, is this. This is what we call radar. See how it kind of changed? This is going to be the model's generated radar. This is not actually currently. Then you have precipitation, which is what we were on earlier. And then you can go through all this list and kind of determine relative humidity is very important for determining. Now, if you left click on an area that you would like to look at, so let's go back to precipitation. Let's left click, say, on around the area of DC. As you can see, this is what we call a sounding, as it says up here in the top left, model sounding viewer. Now this sounding helps modelers, forecasts, all sorts of things. Helps people at the SPC and NOAA determine through the math what some of the values are and how severe things will get. Now, as on the left, you will see a bar from 1,000 to 100. These are millibars. Typically, 1 millibar is about 0 to 100 feet, distance-wise. Over here on our right, you have SRH, 0 to 1 kilometer. The higher this number, the more severe. SRH 0 to 3 kilometer, which is just higher up in the atmosphere. This is about 900 to 800 millibars. In which SRH is very useful. Again, both SRHs, the higher the number, the more severe. You have SB Cape, which is not as important, but is still very important. ML Cape, which is more of a sensitive cape, I do believe. So basically, it won't be as sensitive to lower values. MU Cape, which is going to probably be your most decisive one. MU Cape standing for most unstable, convective available potential energy. CAPE is what we determine as a few factors basically merged into one big calculation. CAPE is basically the intensity and instability. Now, for your SIN, your SB SIN is important because it can cap off storms, which prevents them from going higher into the atmosphere and growing. That is important. I do believe the higher the negative number, the worse it is for storms. It makes more of a cap. And then your RH, which is from 300 to 850 millibars, so from 300 to about 850 right here. RH stands for relative humidity, which is going to be very useful for helping calculate dew point temperature, and will be helpful to determine how strong storms can be. Your P watt. Now, I believe this is precipitation that has fallen over a certain period. Currently, this is 2 inches over DC, or will be 2 inches soon. Now, looking at the actual T-skew, so this thing right in front of you with the lines, this is what we call a T-skew. Down here at the bottom, you can see there's a green, blue, and red line. Your red line is going to be your temperature. The higher up this goes, the more in the atmosphere it goes. Basically, left to right. To the right is higher temperatures, to the left is lower temperatures. So as this is going up, it's getting colder and colder. I do believe your blue line is your SP SIN, and as it looks right now, there is a cap inversion. Again, that's what we talked about with SIN, creating a cap inversion for higher level negative numbers. And one last thing before we get off of this page, this is what we call a hodograph off to your top right. Each number representing a level of the atmosphere going up to 9 levels. Every time this thing makes a curve or a sharp deviation, that is essentially, like for example, there's a hairpin turn here, that is essentially a brand new number of the atmosphere. So basically, it goes 1 through like 12. Now that we've got that settled, to the bottom left is going to be southeast. Basically, I believe it is northeast, southeast, and then, all the 4 main directions. Your equivalent pressure is not typically that important. It can be important, but it's not typically that important down here in the bottom right. And there are multiple other sites that you could choose from. However, Tropical Tidbits is the one we are going to be using in this video. Looking at lower dynamics. At lower dynamics, we have height and wind for 800 millibars. This is kind of like your wind shear, if you know what that is. If you do not know what that is, wind shear is basically the amount of wind in the atmosphere. I do believe it is called shear just because of how quick it can move. But you have your wind shear. Now, again, these can value very high at times. So if we go back to that DC area, we can see that the wind shear is kind of in the 16 to 15 mile an hour range at 850 millibars. Now again, 850 millibars roughly from that area is about 3 or 4 kilometers. And again, there are multiple other dynamic things that you can click. If you want to test them out and look them up on your own, you may. Moving on to upper dynamics, you have your simulated IR satellite. This is basically, if you've ever seen a satellite radar, where it's literally just clouds and then the darkness of the Earth, that is essentially what IR satellite is. It is a generated forecast model for satellite. Now, they do not use these as actual satellite because, as you may know, actual satellite is by the satellite in real time, or near real time. But models can also simulate this too, just to kind of give you a bit more of a look into height of storms and then how big they're going to be as the systems. Looking at upper dynamics one last time, of course you've got your 500 millibar information. Now you do have RH and pressure, and then you've got your pressure and wind. I do believe this one is a upper atmosphere. Also, fun fact, if you left click and drag, you can get an area sounding instead of a specific point. Now, lastly, for your thermodynamics, this is going to be 700 and 850 millibars. This is for temperature and wind. Now, these little wind barbs, which we'll talk about here in a minute, are going to be very important. These wind barbs are going to be pointing in the direction where the wind is not going. That meaning that the wind is going southeast. And of course, there are hundreds of other things you could probably test with on this website and others. However, Tropical Tidbits was just the one we wanted to choose today. Now let's go ahead and move over to something I like to call NAM 3 kilometer. Now, NAM 3 kilometer is going to have a lot less limited range globally. However, it is mainly used for the US anyways. This is where we're going to get a bit more into CAPE and your lapse rates and stuff. 93 kilometers allows us to get a much accurate viewing at them. So, radar and satellite, this is a mix of both radar and satellite, as it says. Your dew point, now this is very important because dew point also helps fuel storms. So, for example, in that Washington, D.C. area, our dew point is roughly in the 60-degree range. Again, which isn't bad, but when it comes to temperature and dew point, you typically want to have anywhere from a 5 to 15 degree difference between the two, as that is the typical best area for CAPE. Looking at lower dynamics, this is pretty much the same stuff we just covered. There is wind specifically though. These are not wind gusts all the time, but these are mainly just constant winds. You got your vorticity and your wind, and then your wind crossovers and SB CAPE. Now moving over to HRRR. This is going to be your most highest resolution, accurate, and your shortest forecast model. For 12Z, for every 6 hours on the Zulu time, they can go up to 48 hours. However, typically they only go up to 18. Hours 0, 6, 12, and 18, you can get up to 48 hours on the HRRR model. Precipitation and moisture, this is going to again include most of the same stuff. Your dew point, your radar, your lower dynamics, and your higher dynamics. Again, mostly just the same stuff, but on a better resolution, that way you can kind of see better detail. That's going to wrap it up for this video, guys. If you want to watch video 2, you may go right ahead. Happy forecasting, guys.